Here's problem 1423. A venturi tube may be used as the inlet to an automobile carburetor. If the 2 centimeter diameter pipe narrows to a 1 centimeter diameter, what is the pressure drop in the constricted section for an airflow of 3 centimeters per second in the 2 centimeter section? Density of the gasoline vapor is 1.2 kilograms per meter cubed. Alright, so we're going to have a pipe that goes from a larger section down to a smaller diameter, and the original diameter is 2 centimeters and the final diameter is 1 centimeter. Well, the continuity equation applies to this. If we call this point A and this point B at the smaller diameter, then it is true that the area at A plus the velocity at A is equal to a constant. It's equal to the area at B times the velocity at B. So the velocity at B is going to equal the area at A divided by the area at B times the velocity at B, or velocity at A. Area at A is going to be pi times the radius at A squared. Area at B is going to be pi times the radius at B squared. All this times the velocity at A. Pi's cancel out. Now the radius at A is half the diameter, so we're going to have that this is equal to half the diameter at A, all that squared, over the radius at B, which is half the diameter at B, squared, all this times the velocity at A. But the 1/2 squares will cancel top and bottom. So this is going to be equal to the diameter at A squared over the diameter at B squared times the velocity at A, which is twice the diameter at B, that quantity squared, over the diameter at B squared times the velocity at A. The diameter at B squares are going to cancel out, and we're going to end up with 4 times the velocity at A, which is going to be equal to 12 centimeters per second. So that is our velocity at point B. Now let's apply Bernoulli's equation. The absolute pressure at A plus 1/2 the density times the velocity at A squared, which is the kinetic energy per volume, plus rho g height at A, which is the potential energy per volume, is equal to the absolute pressure at B plus 1/2 the density times the velocity at B squared plus rho g height at B. But we can define our height, in this case, on a level plane to be 0. So our height at A is 0 and our height at B is 0, and those terms are gone. We want to find the pressure drop, which is going to be the pressure we started with minus the pressure we end up with. That'll be our pressure drop as we go from A to B. So our pressure drop is going to be equal to the pressure at A minus the pressure at B, which from the above equation would be equal to 1/2 the density velocity at B squared minus 1/2 the density velocity at A squared, which is going to equal 1/2 the density velocity at B squared minus the velocity at A squared. 1/2 the density, which is 1.2 kilograms per meter cubed. Velocity at B is our faster velocity, 12 centimeters per second, which is 0.12 meters per second squared, minus our velocity at A, which is 3 centimeters, 0.03 meters squared. And this is equal to 8.1 times 10 to the minus 3 kilograms per meter second squared. I think when they wrote this problem, they intended that it was in airflow of 3 meters per second as opposed to 3 centimeters per second, which would have given us an answer of 81 pascals. Then this times a factor of 10 to the 4. But in this case, this is actually 0.081 pascals would be our pressure drop for this slow of speeds. 0.0081 pascals.